welcome to this problem walkthrough. Today, we'll tackle LeetCode problem number 206, reverse linked list. In this problem, we are tasked with reversing a singly linked list using different approaches. Let's dive into the details and explore how to solve it effectively. In this problem, you are given the head of a singly linked list, and your task is to reverse the list and return the head of the reversed list. A singly linked list is made up of nodes where each node contains two components: the value of the node, an integer between -5000 and 5000, and a pointer to the next node in the list. If a node is the last one in the list, its pointer to the next node will be null. For the output, after reversing the linked list, the function should return the updated head of the list, which now points to what was originally the last node. This forms the basis of the input and output expectations for the problem. Let's look at an example to better understand the reversal process. Imagine the input is a linked list with nodes containing values 1, 2, 3, 4, and 5, connected in that order. Initially, the head of the list points to the node with value 1. After reversing the list, the structure changes so that the node with value 5 becomes the new head, and the order of connections is reversed. The reversed list is now 5 pointing to 4, which points to 3, and so on, until the last node, which is 1, and its next pointer is null. The head of the reversed list is the node with value 5. Consider another example where the input linked list has only two nodes, 1 and 2, connected as 1 pointing to 2. Here, reversing the list involves changing the direction of the connection so that 2 becomes the head and points to 1, with 1's next pointer set to null. The reversed linked list is therefore 2 pointing to 1. In this case, the new head is the node with value 2. Now, let's address the scenario where the input linked list is empty, meaning the head is null. Since there are no nodes in the list, reversing it still results in an empty list, with the head remaining null. This brings us to some important constraints and edge cases. The number of nodes in the list will always be between 0 and 5000, and the node values will range from -5000 to 5000. The input is guaranteed to be a singly linked list, so there are no circular or doubly linked structures to handle. For edge cases, we must ensure that an empty list is properly handled by returning null. A single node list returns the same node, and the solution efficiently handles the maximum limit of 5000 nodes without performance issues. To solve the problem of reversing a singly linked list, we start by considering the iterative approach, which is often the most intuitive. The idea here is to traverse the linked list while carefully adjusting the next pointers of each node to reverse their direction. To achieve this, we maintain 3 pointers: previous, current, and next. Initially, previous is set to none, and current points to the head of the list. As we iterate, we store the next node in a temporary variable, point the current.next back to previous, and then advance both previous and current to the next nodes in the sequence. This process continues until we reach the end of the list. At that point, previous holds the new head of the reversed linked list. This approach is very efficient, as it has a time complexity of O(n), where n is the number of nodes, and a space complexity of O(1), since it requires no additional data structures beyond the pointers we use during traversal. Another method to reverse a linked list is the recursive approach. This technique leverages the power of recursion to simplify the problem. The intuition here is to break the problem down into smaller subproblems. Specifically, we reverse the sublist starting from the second node and then adjust the pointers so that the second node points back to the head. The base case for the recursion is when the list is either empty or contains only one node, in which case the list is already reversed, and we can return the head as is. For the recursive step, we first reverse the rest of the list and then set the next of the subsequent node to point back to the head, disconnecting the head from the rest of the list by setting its next to none. While this approach is elegant and concise, it has a space complexity of O(n) due to the recursion stack, in addition to the O(n) time complexity required to visit each node once. An alternative technique we might consider is the stack-based approach. In this method, we use a stack data structure to help reverse the list. The intuition is straightforward: as we traverse the list, we push each node onto the stack, effectively storing the nodes in reverse order. Then, by popping the nodes off the stack one by one, we can reconstruct the linked list in the reversed order. While this approach is easy to understand and implement, it is suboptimal in terms of space complexity because the stack requires O(n) additional space to store all the nodes. The time complexity, however, remains O, n, as we still traverse the list only once and process each node exactly twice, once when pushing it onto the stack and once when popping it off. This method is less commonly chosen in practice due to its higher space requirements compared to the iterative approach. Among the approaches we've discussed, the iterative approach emerges as the most practical and efficient solution for this problem. Its simplicity lies in the straightforward traversal of the list while adjusting pointers, and its efficiency comes from requiring O, n, time and only O, 1, space. On the other hand, while the recursive approach is elegant and aligns with a divide-and-conquer mindset, it introduces the overhead of the recursion stack, which makes it unsuitable for very large lists due to the risk of stack overflow. The stack-based approach, though intuitive, is generally less efficient because of the extra space it requires for the stack. In summary, the iterative approach strikes the best balance between simplicity, efficiency, and robustness, making it the preferred choice for most use cases. Reversing a linked list boils down to a key insight: the operation revolves around adjusting the next pointers of nodes rather than creating new nodes or data structures. This realization simplifies the problem significantly. The iterative solution stands out as the most efficient and reliable method, as it avoids unnecessary overhead and handles edge cases gracefully. While the recursive approach offers a clean and concise implementation, its reliance on the recursion stack makes it less memory efficient and potentially problematic for large input sizes. The stack-based approach, though useful for educational exploration, is suboptimal due to its O, n, space complexity. By selecting the iterative approach, we achieve an optimal balance of simplicity, efficiency, and practicality, making it the best fit for the problem's constraints and typical usage scenarios. To reverse a singly linked list, we need to change the direction of the next pointers for all nodes in the list. The goal is to make the last node of the original list the new head, and the first node the new tail. To accomplish this, we use an iterative approach with 3 pointers: previous, cur, and next underscore node. Initially, previous is set to null because there is no node before the head at the start. Cur is set to the head of the list, as this is where we begin traversal, and next underscore node will be used to temporarily store the next node during the process. The key is to traverse the list node by node, reversing the direction of the next pointer for each node, all while ensuring we don't lose access to the rest of the list. This setup will allow us to systematically reverse the list in place. Once the pointers are initialized, we enter the core traversal loop. While the cur pointer is not null, we proceed with the following steps. First, we save the next node in next underscore node using cur.next. This is critical to ensure we don't lose access to the remaining nodes after reversing the current pointer. Next, we reverse the next pointer of the current node by setting cur.next to previous. This effectively flips the direction of the link for the current node. Then, we move the previous pointer forward by assigning it to cur, making it the new previous node for the next iteration. Finally, we advance cur to next underscore node, which we saved earlier, so that we can process the next node in the original list. When the loop ends, cur will be null, and the previous pointer will point to the new head of the reversed list. At this point, we return previous as the result. This approach ensures that the entire list is reversed efficiently in O, n, time, using only O, 1, extra space. The process of reversing the list hinges on 3 key operations. The first is pointer reversal, where we set cur.next equals previous. This step is crucial because it changes the direction of the link for the current node, starting the process of reversing the list. The second operation is traversal, where we advance the cur pointer by assigning cur equals next underscore node. This ensures that we continue processing each node in the original list without skipping any. The final step is updating the head of the list. At the end of the traversal, the previous pointer will point to the new head of the reversed list, and returning previous completes the reversal. Now, let's consider some edge cases. If the list is empty, where head is null, the algorithm will simply return null. For a single node list, reversing it has no effect, and the algorithm handles this naturally. For lists with multiple nodes, the algorithm works seamlessly to reverse the links, regardless of the size of the list. This robustness makes it suitable for a wide range of scenarios. Here's the Python implementation of the algorithm. We define a reverse list function that takes the head of the list as input. Inside the function, we initialize previous to none and cur to the head of the list. Then, we enter a while loop that continues as long as cur is not null. Within the loop, we first store the next node using next_node equals cur.next. Next, we reverse the link by setting cur.next equals previous. Then, we update previous to point to the current node and move cur to next_node to continue the traversal. Once the loop ends, we return previous, which now points to the new head of the reversed list. This concise implementation directly applies the iterative process we discussed, and it effectively reverses the list in place with optimal time and space complexity. This Python implementation reverses a singly linked list using an iterative approach. The reversal is achieved by manipulating the next pointers of nodes in the list. Here's the step-by-step explanation. 1. Node class definition. The list node class is used to define the structure of a linked list node. Each node contains a val, its value, and a next pointer to the next node. 2. Initialization. The reverse list function starts by initializing two pointers. Previous, set to none initially, representing the tail of the reversed list. Cur, set to the head of the original list, representing the node currently being processed. 3. Traversal and reversal. The while cur loop ensures we traverse until all nodes are processed. Inside the loop, next_temp temporarily stores the next node of cur to avoid losing the link. Cur.next equals previous reverses the next pointer of the current node to point to the previous node. Previously is updated to cur, effectively moving the previous pointer forward. Cur is updated to next_temp, moving the cur pointer forward for the next iteration. 4. Returning the new head. When the loop ends, previous points to the new head of the reversed list, which is returned. This algorithm runs in O(n) time complexity because each node is visited once, and it uses O(1) space complexity as no additional data structures are used. This makes it efficient and well suited for reversing a singly linked list. Here, we have the Java implementation for reversing a singly linked list. First, we define a nested static class called listNode, which represents the structure of a node in the linked list. Each node contains an integer value and a reference to the next node. The constructor initializes the node's value and sets the next reference to null. Now, in the reverse list method, we start by initializing two pointers, previous, which is set to null, and cur, which is set to the head of the list. These pointers will help us traverse and reverse the list. The key operation happens inside the while loop, which continues as long as cur is not null. Within the loop, we first save the next node by assigning cur.next to a temporary variable, nextTemp. Then, we reverse the current node's pointer by setting cur.next to previous. After that, we move the previous pointer forward by assigning it the value of cur, and finally, we advance the cur pointer to nextTemp. This process ensures that each node's pointer is reversed one step at a time while traversing the list. At the end of the traversal, when cur becomes null, the previous pointer holds the new head of the reversed linked list. This is because previous points to the last node that was processed in the loop, which is now at the start of the reversed list. The method returns previous, completing the reversal. This approach uses an iterative method to reverse the list, and it operates in O(n) time complexity, where n is the number of nodes in the linked list. Additionally, it uses O(1) space since the reversal is done in place without any auxiliary data structures. This makes the solution efficient and well suited for most practical scenarios. Here, we begin with an example of reversing a linked list with multiple nodes. The input linked list is 1 2 3 4 5. Initially, we set previous to none and cur to the head of the list, which points to 1. In the first iteration, we store the next node, 2 3 4 5, in next_temp. We then reverse the direction of the cur node by setting cur.next to previous, making 1 point to none. Next, we move previous to the current node, which is now 1 none, and shift cur to next_temp, which points to 2 3 4 5. At this point, previous is 1 none, and cur is 2 3 4 5, reflecting the partial reversal of the list. In the second iteration, we store the next node, 3 4 5, in next_temp. Then, we reverse the current node by pointing cur.next to previous, making 2 point to 1 none. After that, we move previous to the current node, updating it to 2 1 none, and shift cur to next_temp, which points to 3 4 5. Now, previous is 2 1 none, and cur is 3 4 5. Moving on to the third iteration, we repeat these steps. We store the next node, for 5, in next_temp, reverse the current node by pointing cur.next to previous, making 3 point to 21 none. Then, we update previous to 321 none, and cur to next_temp, which points to 45. By the end of this iteration, previous is 321 none, and cur is 45. In the fourth iteration, we store the next node, 5, in next_temp. We reverse the current node by making cur.next point to previous, which results in 4 pointing to 321 none. We then update previous to 4321 none and move cur to next_temp, which points to 5. At this stage, previous is 4321 none, and cur is 5. In the fifth and final iteration, we store the next node, none, in next_temp. We reverse the current node by pointing cur.next to previous, making 5 point to 4321 none. Finally, we update previous to 54321 none, and cur to next_temp, which is now none. At this point, the loop ends, and the reversed linked list is 54321, with previous pointing to the new head of the list. Now, let's look at an example with a single node linked list. The input linked list is just 1. Initially, previous is set to none, and cur points to the head of the list, which is 1. In the first and only iteration, we store the next node, which is none, in next_temp. We then reverse the current node by pointing cur.next to previous, making 1 point to none. Next, we update previous to the current node, which is now 1 none, and move cur to next_temp, which is none. Since cur is now none, the loop exits. The final state shows previous as 1 none, and cur is none. The reversed linked list is simply 1. Finally, we consider the case of an empty linked list. Here, the input list is none. Both previous and cur are initialized to none. Since cur is already none, the while loop does not execute. The function immediately returns previous, which remains none. This means the output linked list is also none, as there were no nodes to reverse. The time complexity of the reverse list function is O(n), where n represents the number of nodes in the linked list. This is because we traverse each node exactly once, performing a constant amount of work during each iteration. To break it down, the while loop continues executing as long as the cur pointer is not null. Starting at the head of the list, cur moves to the next node in every iteration. Inside the loop, we execute 3 primary operations: accessing the next node, reversing the current node's pointer, and updating the previous and cur pointers. Each of these operations is O(1). Since we execute these operations n times, once for each node, the total time complexity is O(n). Importantly, this runtime does not change based on the input structure, it solely depends on the size of the linked list, making it consistent across best, average, and worst case scenarios. The space complexity of the reverse list function is O(1), meaning it uses a constant amount of extra memory regardless of the size of the linked list. This efficiency comes from the fact that the algorithm does not rely on any auxiliary data structures like arrays or stacks. Instead, it only uses 3 variables: previous to store the previous node, cur to track the current node, and next_temp to temporarily hold the next node during pointer reversal. Since these variables occupy a fixed amount of memory, the space usage stays constant. This makes the iterative method highly space efficient compared to other approaches that require additional memory proportional to the input size. Let's compare the iterative approach to 2 common alternatives. A naive or brute force method would involve using an auxiliary data structure like a stack or array. In this approach, we first traverse the linked list and store all nodes in the stack, which requires O(n) space. Then, we reconstruct the reverse list by popping nodes from the stack, which takes O(n) time. While the time complexity is still O(n), the space complexity increases to O(n) due to the additional storage. Another alternative is the recursive approach, which reverses the list by recursively calling the function on the remaining nodes. While this also has a time complexity of O(n), the space complexity becomes O(n), because each recursive call adds a new frame to the call stack. In contrast, the iterative method achieves the same time efficiency with constant space, making it the most space-efficient solution. To mathematically prove the big O complexities, let's start with time complexity. Denote T(n) as the total time the algorithm takes for a linked list with n nodes. Since the algorithm performs O(1) work in each iteration and iterates n times, the total work can be expressed as T(n) equals O(1) plus O(1) plus O(1) repeated n times. This simplifies to O(n). For space complexity, the proof is straightforward. The algorithm only uses a constant number of variables, previous, cur, and next underscore temp, regardless of the size of the input. This fixed memory usage means the space complexity is O(1). Combined, these proofs confirm that the iterative approach is both time-efficient and space-efficient. When working on reversing a linked list, there are several common mistakes that can trip you up. First, modifying the next pointers without saving them is a frequent error. If you update current.next without first storing its original value, you lose access to the rest of the list, making it impossible to complete the reversal. The solution is simple: always save current.next in a temporary variable before making any changes. Another mistake is failing to update the previous pointer in the iterative approach. Remember, the previous pointer is crucial for maintaining the reversed order of the list, so it must be updated alongside the current pointer in each iteration. Lastly, some forget to set the next pointer of the new tail node, previously the original head, to none. Leaving it unchanged can create cycles in the list or lead to unexpected behavior during traversal. Always ensure the new tail's next pointer is explicitly set to none to avoid such issues. Recursion introduces its own set of challenges, one of which is confusing the base case. A common mistake is mishandling the base condition, such as returning none instead of the last node. This could result in infinite recursion or incorrect outcomes. The correct approach is to return the current node when current.next is none, which signifies the end of the list. Another easily overlooked issue is assuming the list is non-empty. Edge cases like an empty list or a single node list need to be handled explicitly. Without these checks, you risk running into null pointer exceptions or segmentation faults. To prevent this, add conditions to handle scenarios where the head is none or the list contains only one node before proceeding with the reversal logic. In interviews, simplicity is key. While both iterative and recursive approaches are valid, interviewers often favor the iterative method for its clarity and in-place reversal. If you opt for recursion, be prepared to explain how the recursion stack works and discuss its space complexity. Always address edge cases, ask the interviewer about handling empty lists, single-node lists, or extremely large inputs. This shows attention to detail. Additionally, make sure you can clearly articulate how you manage pointers like current, previous, and next during the reversal process. Being able to explain the step-by-step updates demonstrates a strong grasp of the concept. Finally, discuss time and space complexity. While both methods have O(n) time complexity, the iterative approach is more space-efficient with O(1) space, whereas recursion incurs O(n) space due to the stack. Highlighting these trade-offs can set you apart in an interview. There are several related problems that can deepen your understanding of linked list manipulation. For instance, LeetCode 92 involves reversing only a sublist within the linked list, which is a great extension of this problem. LeetCode 21 focuses on merging two sorted linked lists, which provides additional practice with pointer manipulation. LeetCode 24 challenges you to swap nodes in pairs, and LeetCode 234 involves checking if a linked list is a palindrome, requiring you to reverse just the second half of the list. As for alternative approaches, the iterative method is the most efficient in terms of space, requiring O(1). It's generally the go-to solution due to its simplicity and efficiency. Conversely, the recursive method, while conceptually elegant and sometimes easier to write, uses O(n) space because of the recursion stack. This makes it less efficient for very large lists but may still be preferred in scenarios where recursion aligns naturally with the problem requirements. Lastly, there's the option of creating a new list instead of reversing the original one. This approach involves constructing a completely new linked list by traversing the original list and inserting nodes in reverse order. While this method ensures the immutability of the original list, it comes with a significant trade-off: it requires extra space, specifically O(n), to store the new list. This makes it less efficient than in-place reversal. Creating a new list is rarely used in practice due to its inefficiency, but it might be acceptable in cases where immutability is a strict requirement. Understanding this alternative approach gives you a broader perspective on solving linked list problems, even though it's not the most practical solution in most scenarios. To summarize, we reviewed the iterative approach for reversing a linked list, covering its time and space complexities. Key takeaways include the importance of pointer manipulation and mastering linked list fundamentals. Thank you for watching. Don't forget to like, subscribe, and stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!